For this lesson, we're going to be looking at the idea of modeling using a quadratic equation, and in particular, we're going to be modeling using quadratic equations in the vertex form. So that's going to be in the form y equals a x minus h all squared plus k. Now, what does it mean to model when we talk about modeling quadratics? Modeling a situation in general, this isn't just for quadratics, this is for any type of equation. And so what that means is you've got some sort of situation, you've got some data. For example, you might be given a graph, you might be given a verbal description, you might be given a set of numbers that somehow connects to each other. And so to come up with a model essentially is to come up with the equation that can be used to describe that. Now, a model can be a good or bad model. A model can be good or bad depending on what kind of model you choose. So there are lots of situations where a quadratic model is a terrible model. The only other model we've really talked about so far is linear, but there are many other types of equations out there, which means there are many other ways to model data. We're going to focus, of course, on quadratics. So in the case of a quadratic, let's imagine it's a picture or something that can be described with a picture. If at all possible, try to come up with at least a sketch of the parabola that applies to the given data or the given situation. If the graph is given to you already, all the better. Identify the key properties if you can. So the key properties are going to be, the most important one is going to be the vertex. You might be interested in the y-intercept. Don't ignore things like the direction of opening, because whether it opens up or down, at least that gives you an idea about the sign of A, whether or not A is positive or negative. And that comes down here to the last point. Does your answer make sense? So the more information you can extract from your initial situation, the better idea you'll have when you get to the end as to whether or not that's a reasonable answer. Another piece of information you're going to be interested in, if you can read it, is the zeros. You don't necessarily have to list these things, but you need to do a mental check, make sure that you can find these different values. Another one, well, if you can get the vertex, zeros. Another thing we might put in here is the axis of symmetry. Let's see what else. Max, min, that kind of goes, I'll still put that in. So the maximum or the minimum. All of those things, they're all fairly fundamental ideas when it comes to parabolas, and you need to visually, or maybe you even write these down. If we have the vertex, we're a long way towards being done, because then we can sub our vertex directly into vertex form, and once we have vertex form, all we have to do is sub another point. So any other point means you can't use a point that you've already used. So for example, if you had the vertex and you subbed it in here, you can't sub in the vertex again. We did something similar with factored form. If you have the zeros and you write factored form, when you're trying to find A, you can't use the zeros again. They get used up in writing the equation. If you didn't have the vertex, if, for example, the axis of symmetry is just the x-coordinate of the vertex. That's just the h value from the vertex. So if you only had something like that, you actually might need to sub 2 points into your equation. Because let's say we had the h, well then we don't have k and we don't have a. We would have to create a system of linear equations and solve that using some concepts we've learned at another time in the course. And then you ask yourself, does this answer that I've come up with make sense? Okay, let's start off with a very straightforward question. And we're going to take a note of some of the things that are given. Very clearly here I have my y-intercept, and it is at the point 0, 5. So that's my y-intercept. And this graph is a nice graph in the sense that we've got points that are on exact grid crossings. Sometimes you'll get a graph that's not nearly so exact. You're just approximating a parabola, and then you might have to come up with an estimate. Here I can say with quite a bit of confidence that I have my vertex is at x equals 2, y equals 1. And if I need it, There's another good point at a grid crossing. There's another good point at a grid crossing. By symmetry, we have another point up here at a grid crossing. So lots of good information here. My parabola opens up, so that means I would expect my A value to be positive. My A value should be greater than 0. And we'll just use that as a confirmation when we do our results here. So let's start with the general equation in vertex form. X minus h all squared plus k. And then I'm going to sub my vertex, which is the point 2, 1. So now I have y equals a, and instead of x minus h, it's going to be x minus 2 all squared plus k, which is plus 1. And now in order to find this a value, which is currently unknown, I need to sub another point. Now it turns out the y-intercept has a 0 in it, so that makes it a pretty simple point to make use of because the x value is going to be 0. So that becomes 5. There's the x value, there's the y value. So the y value goes here, becomes 5. And then we have a, which is what we want to solve for. X minus 2 becomes 0 minus 2, all squared, plus 1. And I'm not going to skip any steps here. Well, maybe I'm going to skip one, which is negative 2, 0 minus 2 all squared. That's equal to 4 plus 1. I guess I didn't really save any trouble there because I'm going to rewrite this as 4a plus 1. And I bring this positive 1 to this side, and that becomes 4. 5 minus 1 is 4 equals 4a. Divide both sides by 4, and I end up with a equals 1. Not with a decimal. And since a is equal to 1, my equation is simply y equals x minus 2 all squared plus 1. And as I said at the end of our note, why don't we make sure that makes sense? We take a look. We did end up with a being positive, so that's a good thing. If this is a value of 1 in front, then what does that tell us? Says that this parabola has not been stretched or compressed with respect to the parent function. So if that's the case, then the step pattern should be the same, which should be over 1, up 1, over 1, up 1, 2, 3. Oh, okay. Left 1, up 1, left 1, up 1, 2, 3. So the step pattern is the same as the parent function, and so that is consistent with this value of 1. So I'm pretty happy that this equation correctly describes this parabola. Let's do another example. Here we don't have a picture. State the equation of the parabola obtained by applying these transformations to the graph of y equals x squared. We have a vertical stretch by a factor of 5, a vertical shift of 9 units. So for this one, it says a vertical shift of 9 units. And just to make sure that one's clear, because I usually try to represent things this way, I would call that a vertical shift up by 9. Okay? Because this is positive here. Some people have asked that in class, and I've really discouraged people from actually writing it that way. So I apologize that it's appearing here in the notes. Okay, a sketch is a good idea. I'm not going to use a grid. I'll just put in something very rough. And what do we have here? Well, first of all, let's just put in a sketch of the parent function. And what has happened to it is it has been stretched by a factor of 5 and it's been shifted up by 9 units. So that means this 0, 0 has moved up here. And now it's really tall and really skinny. So that's at 9. Okay, so what does that actually tell us? Well, even just by drawing it like this, shifted up by 9, well, now we know actually where the vertex is. The x-coordinate of the vertex is still 0. The y-coordinate of the vertex is 9. And a vertical stretch by a factor of 5, there's nothing mentioned about a reflection here. So that actually tells me that my a value is 5. So if I start with the generic x minus h all squared plus k, then I can go ahead and make some substitutions. Instead of a, I can put this value of 5. X minus, it's going to be x minus, but instead of h, so that's hk. Don't forget the x coordinate and y coordinate are h and k. So this becomes x minus 0, all squared, plus k is the value 9. And we don't normally represent x minus 0 as anything other than x. So this whole thing just becomes x squared. And so my equation in its final form is 5x squared minus 9. And does that make sense? It's still positive, opening up, and it's been shifted, and I actually made a small mistake there. I changed that plus to minus. It's plus 9. Maybe I would have caught that, but seeing the diagram there certainly didn't hurt. Okay, and write a possible equation. Now I've emphasized the word possible here. That means that there are actually many answers for this one. We want a parabola that has a vertex at negative 3, 5. It has no zeros. That's interesting. And it's wider than the parent function. So again, I'm going to do a quick sketch. Part of the reason for this sketch is just to make sure I have my head wrapped around what the question is actually asking for. So again, I'll just put in a sketch of the parent function. I'm not putting on a scale or anything like that. Just putting in the parent function, and let's try to figure out what this other one's going to look like. Negative 3, positive 5. So I'm just going to arbitrarily put that there. And it has no zeros. Now that's interesting. No zeros means that it can't open downward, because if it opened downward, it would cross the x-axis. So if it has no zeros, and it's obviously not touching the x-axis, it has to open upward. And it's wider than this one. So it's not opening upward like this. It's opening up more widely than the blue one. So I'm really going to exaggerate that, and I'll just do this and that. Actually, maybe that's a little too much, since it's taking up, now I'm just making it worse. Okay, that'll have to do. It is just a rough sketch. So let's see what we can do to get all of these things working together. Y equals a bracket. Now I'm going to go straight to, well, I guess I'm not going to take too much of a shortcut. It's x minus, and I'm going to put this x value in here. So for the vertex, that's negative 3, all squared, plus, and then the k value, which is just positive 5. So I just go ahead and write a 5 there. Let's clean that up. It becomes a x minus negative 3 becomes x plus 3, all squared, plus 5. And now that we've done this, we have to figure out our a value. But we don't figure out our a value by substituting. Because it's a possible equation, there are actually many possible answers. There are an infinite number of answers. We just have to pick an a value that is consistent with this graph. So what can we tell from this graph and this piece of information? No zeros, wider than. Well, the no zeros part, let me just move this down a bit so I can actually put a note underneath. No zeros tells me this thing has to open up. That's the only way to avoid zeros. So opening up means that a has to be a number bigger than 0. It's wider than y equals x squared. That one means that it is compressed. And the way that we get compressed is the absolute value of a has to be less than 1. So how do I combine these things together? So what are some possible values of a? A could be equal to, what would make sense? A positive number that's less than 1. Well, one that we've used many times is 0.5 or a half. But we could also do things like 2/3 or 1/10 or 1/500. Any of those would be fine. 0.999 would be fine, so long as it's positive, but it's less than 1. So I'm just going to go with our standard 1/2. So we end up with y equals 1/2 x plus 3 all squared plus 5. Last example, a little bit more sophisticated. Find the equation of the quadratic that passes through these points. Now, notice it never said anything about a vertex, so we can't assume anything about a vertex here. And notice that we don't have zeros. Now, in the note at the beginning, I made a reference to the word symmetry. And the place where we have dealt with symmetry up until now has always had to do with the zeros. But here I'm not actually giving you the zeros. So how can we make use of this idea of symmetry? So let's go ahead and graph, at least let's plot these points, get a rough idea. So -3, 2. So now I think it's worth it to put a bit of a scale on here. So I'm going to shift things over a bit. I can see that I want -3, 2. So 1, 2, 3, and then up 2. And yes, I could put a grid on here just as easily, but I want to show you that even if you're doing this by hand, just doing a quick sketch, you can still kind of space these things out just by hand, trying to keep them even. So this one's at 5, 2. And then we have 7. So there's 7, there's 5, there's -3, there's 2, and then we've got a point at 7, 4. So you can see you can do a reasonable job even if you don't put a grid on there. Now, the idea of symmetry. We are going to use symmetry here even though we don't have any zeros. Now, how is that possible? The reason why symmetry will work here is because I don't have a very nicely colored line, so I'm just going to freehand this in. The reason why symmetry is useful or valuable here is because these 2 points have the same y value. So the same y value. And in this case, it's y equals 2. So this point and this point, so the points -3, 2 and 5, 2 are symmetric. Okay, so what that means, the fact that those 2 points are symmetric, the fact that they're at the same level, means that the axis of symmetry is halfway between them. So in the past, we've always talked about the axis of symmetry. When you're finding the axis of symmetry, it is simply the x-coordinate of the midpoint. Well, what is the x-coordinate of the midpoint of these two? Just like we do with zeros, we take the x-coordinate -3, we add the other x-coordinate +5, divide that by 2. -3 plus 5 is 2 over 2, and that's equal to 1. So the axis of symmetry is at x equals 1, but that means that the x-coordinate of the vertex is equal to 1. So we actually have half of our vertex now, and our graph, so it's at 1, so here's 1. So I'm just going to draw a vertical line now. That's my axis of symmetry. And so my parabola has to go through these 3 points and through here. So I'm just going to kind of guess, and I'm going to put a vertex there, and I'll draw my parabola like that. Sorry, not a very symmetric parabola. You'll have to forgive me. So now this is very much of a guess. I want you to understand that this vertex might be above the x-axis, it might be below. So don't read too much into this. The important part here is that we know that the x-coordinate of the vertex is 1. So that being said, now I can go to my equation, y equals a x minus h all squared plus k. and I can immediately say that this is actually x minus 1 all squared plus k. That's from the axis of symmetry. So right there is the axis of symmetry going in there. Now that I've done that, well, you can see my unknowns are a and k. So I actually need to sub 2 points. So we have to sub 2 points, and then we're going to have to solve a system of equations. So let's sub, sorry, I wanted to switch colors there. So we'll sub, and if we look at points, there's nothing really to make them easier or less easy except for this one has a negative sign in it, so I'm going to use only positive values. So I'm going to sub 5, 2, and that gives me the y values 2, so I get 2 equals a bracket 5 minus 1 all squared plus k. And that gives me 2 equals 5 minus 1 is 4 squared. 4 squared is 16, so we end up with 16a plus k. Call that equation number 1. Now we're going to sub the point 7, 4. And so now our y coordinate becomes 4, a bracket, now it's going to be 7 minus 1 all squared plus k. Myself some more room here. 4 equals 7 minus 1 is 6. 6 squared is 36. So this one becomes 36a plus k. Call that equation 2. And now we're doing a system of equations very much like what we did in a previous unit. So we need to take equation 1 and equation 2 and solve them. Well, I think the best way to do that, we could do elimination. How can I line these up? Well, actually, they already are lined up. The k values are already lined up. So I'm just going to rewrite equation number 1 right here, 16a plus k. So that's still equation 1. And then I'm going to subtract. So I'm going to do equation 2 minus equation 1. Normally I write this on the left. There's not a lot of room there. 4 minus 2 is 2. 36a minus 16a is 20a. And then k minus k is 0. So now we just have a by itself. Divide both sides by 20. And we end up with a equals 1 over 10. Which is not a very nice fraction, but it's workable. So now that we have a equals 1 over 10, my equation becomes y equals 1 over 10 x minus 1 all squared plus k. And now we just need to find this value for k, and I can sub any point. So I will sub, I think the easiest point out of all the ones we have is 5, 2. I just want to confirm that that's actually the point. 5, 2. And so I end up with 2 equals 1 over 10, 5 minus 1, all squared, plus k. 2 equals 1 over 10. 5 minus 1 is 4. 4 squared is 16, plus k. I notice that 10 and 16 are both even, so 2 goes into 10 5 times, goes into 16 8 times. This isn't very nice, but it's what we have to work with. So I get 2 equals, this is going to become 8 over 5 plus k. I'm going to take this to the other side, which means I need a common denominator of 5. So I might as well change this 2 over 1 into something over 5. So 2 over 1 is the same as 10 over 5 minus 8 over 5. I took this over to the other side, equals k. And k is equal to 10 minus 8 is 2 over 5. So that gives me my equation of y equals 1 over 10 x minus 1 all squared plus 2 over 5. Okay, and that's not a very nice equation, but it is what it is. And so what does that tell us? The location of the vertex is actually at x equals 1 and y equals 2 over 5. So my graph was wrong. If I go all the way back up here, my estimate. So it's actually, it turns out that the vertex is actually way up here, just above the x-axis. So what I've drawn here is actually incorrect. Let's see if I can just take out that drawing. And so the actual correct drawing should have been from here, looking something more like that. Okay, so there we go. We've got the equation of the quadratic that passes through those 3 points. And you can see that turned into quite an involved solution using multiple concepts and really introducing this idea of symmetry for the first time. We've used symmetry, but the idea of using it generically, using it with any 2 points that are at the same y level or the y value. You can use symmetry whenever you have that. Instead, it doesn't always have to just be the zeros. And that's particularly important because, as you can see in this case, it doesn't actually have any zeros. So the only option to use symmetry here was to use the symmetry of 2 other points. I believe that's it. Should be just homework next, and there it is.